All right, so this number right here is where the tangent line is hitting the axis. That's what that number is. Now we're hoping that that's the same as where the curve is hitting the axis. But we won't know until the tangent lines keep giving us the same number. They keep hitting the same place. Then we know the tangent line, because what we do know about this scenario, what we do know about a tangent line and a curve is when they are close to the point of tangency, we do know that when we have a curve and we have the tangent line, we do know that right in that vicinity, the curve and the tangent line are basically the same thing. That's what we're using in Newton's method. So if the tangent line's touching the axis and we keep getting the same thing over and over, then that means the curve is right there as well, and the curve is hitting the x-axis there also. So that's the idea behind what's going on. Okay, keep going, Allie. Keep hitting enter. Let's get decimals. Go ahead, enter, enter, enter. And there, eventually, we find one of the roots. Is that doesn't look right. Is your function, hit F, type f of x and hit enter. Just type f, no, don't define it, just type f of x and hit enter. That's right, isn't it? Oh, it's minus 10x squared. It's all right. And it's possible then your g maybe isn't quite right either, right? And then plus 22x plus 6, okay? No problem. And then g there we go. Okay, now start with a 6. And then paste that thing. All right, here we go. That looks better. Okay, so that's one of them. That's one of the roots. Okay, now let's try -6 just for the heck of it. And I think we know there's 3 roots. Well, they told us there were 3. So if we start with -6, and again, this number is where that tangent line is hitting the axis. The next number is where that tangent line is hitting the axis, and we keep getting this, and there's the other one, or one of them. And then the last one was around 3. Is that right? So we can go 3, and then, and again, I already knew that ahead of time, kind of where they were, so you could just be blindly guessing around for a while, but anyway, there's the other. Okay, now the second question, and these would be the ones, so what I might do, since it's no calculator, what I might do is give you a screenshot of something like this and ask you to describe what happened, right? In other words, where I give you that formula of Newton's method, go ahead and hit, well, let's move on to part B. Okay, so it says put in a 2. Okay, so you put in a 2 for the guess, and now you do Newton's method. Do it one time. And I might give you something like that. And I might just say this, and here was this function, and now hit it again. You know, and I might give you a screenshot of that and have you describe what's happening or something like that, right? Now, what is happening here? The spinning, the loop, the cycling. Right, it's going back and forth, right? This, and a picture would be a great thing to do to help explain this, right? You're putting in a 2 first, because that shows me you're getting, you don't want to just say it's cycling. I mean, then you just memorized what we're saying in class, and you're not necessarily showing me you know what's going on. So show me a picture of a function where you put in a 2, right? The tangent line goes over here to 5, and then the tangent line goes back to 2. That's what's happened. The tangent lines are crossing at those places back and forth. Okay, and the last one we were supposed to put in what? 1.39, I think? Put in 1.39 and bring up Newton's method, and then just stop after 1. And then maybe I give you this screenshot and I say, what happened here? They said it behaved oddly. What's going on? Because this number is where the tangent line is hitting the x-axis. Way out there at 5,391. Keep hitting enter, and we can see the tangent lines are coming back now getting closer back into, but it takes a long time, right? It takes a long time. Yeah, and eventually we end up finding the one that we already knew existed that we had found earlier, okay? And it finds that root. It eventually will get there, okay? So that would show me you understand the process. Things like that would show me you understand the process of what's going on with Newton's method. Okay, let's switch gears to the packets. Kind of your last day, I suppose, to ask about sample 1 and sample 2, because tomorrow we'll be moving on. I did want to talk about one problem in sample 2. Let's start there. The other class asked about it. I've had a few people in this class ask about it, so this is free response number 3. It's on page 64. Might keep you connected here, Al, in case we need something on the calculator later. Okay. All right. So it talks about graphing them. So that's just plugging a 1, a 2, a 3 in for B, and then just using your calculator. But now the rest of this problem, to me, would be a no calculator problem in this day and age. I don't think they would ask this question. These workbooks are a little older, and they've changed their philosophy a little bit because of the calculators like we have, these CAS calculators. They can do this algebra stuff. Because this is one of the first ones we run into where we have this B, and it's pretty typical that my calc classes struggle in the beginning with problems where they put a K or a B or an A or some letter in there. And we tend to freak out and panic a little bit and not know what to do. And so hopefully, through the course of doing these, we start to get more comfortable with that, kind of like the Shanghai situation. I think we're getting a little more comfortable when we see that and being able to deal with it. So here's what I would say. So in B and C, it says find the XY coordinates of the relative max, relative min. Now what's relative max mean? Local. This is a local max problem. Now forget the B for a minute. How do we go about finding a local max? Derivative equal to 0, solve for x, do a number line. Not a list of candidates, number line, right? Number line is how we do local max min. So forget that there's a B. Just think this is the steps I do. So we're going to do f prime, which is going to be 3x squared. Now we do have to talk about this B here from the sense that it's just a constant. So 3b just would stick together. So what's the derivative of 3bx? Just 3b. So this would be minus 3b, and we set it equal to 0. Now what do? Solve for x, which means get the x by itself. So now, see, with your calculator, since this did say use a calculator, your calculator will solve this. You can tell it to solve for x, and it'll solve it in terms of b. But I think we should practice it as a no calculator because that's how this test is going to be. And if I were making, which I am, making up the midterm, I would put this question in the no calculator. I wouldn't have asked this first part, and then I would have put it in the no calculator part. Okay? So we go ahead and we add 3b over, we divide by 3, and we do the square root, and we get plus or minus square root of b. Very important that we put the plus or minus in. Okay? All right. Now, what did we say was next? Number line. A number line is next. Now, it seems weird to put B's and K's and A's on a number line, but we do. We put them on a number line just like they were regular numbers. So you'd have negative root B. Now, we do know that B is positive. They did say that up in the directions. So B is positive. So we got this. Okay? Now, what's the number in between them? 0. Now, this is the interesting part. What's bigger than square root of B? Okay, you all have some valid points. Here, let me tell you the ones I heard. I heard B. That's not true. That's the one, that's the most common one I hear people say. You say when you square something, what happens to it? Gets bigger. But what if it's less than 1? What about 1/4? Or excuse me, 1/2. What is 1/2 squared? 1/4, it gets littler. So when you square a number, it doesn't necessarily get bigger. Because we don't know if b is bigger than 1 or less than 1, right? So squaring, we want to stay away from. I heard square root of b plus 1. I would agree with that. That does get bigger. But here's the problem with that. Because whatever number we put over here that's bigger than square root of b, what are we going to do with that? Plug it back into f prime, right? Remember, on a number line, we plug, I should have labeled this, we plug back into f prime because we're trying to see if f prime is positive or negative. It's not listed candidates. We're not plugging back in the original right now. We're plugging back into f prime. Well, if I plug into f prime, I got to square it. Well, squaring this would be kind of a pain because it would be a FOIL thing, right? So that wouldn't be a lot of fun. So I would usually avoid the adding. So I heard it earlier, and I ignored you because I wanted to hear the other answer. But 2 square root of b will work. Think about it. If you have any positive number, if you times it by 2, it gets bigger for sure. And same thing's true on the other side. Negative 2 square root of b would be left of negative square root of b because you multiply by 2 and it goes farther left. So those are the numbers I think you want to use. So stay away from the squaring, stay away from the adding, because that tends to get us in trouble. All right, so now we have numbers we can plug in, and it turns out they plug in pretty nicely. 0 is an easy one to start with, so we plug it in where now? Where do we put it? For the x. Put a 0 in for x, you get negative 3b. What is that? We know that's negative because remember they told us b was positive. So negative 3 times a positive is going to be negative. All right, 2 square root of b. Now, it seems a little messy, but it's actually not bad. 2 square root of b, what happens when you square it? 4b times 3, 12b. Take away 3b, 9b, which is positive. So that will be positive for sure. And then negative 2 square root of b, same thing, because we're going to square it, so the negative won't matter. So it's going to be 4b times 3 is 12b. 12b, take away 3b, is 9b. So it's going to be positive. So as you notice, most of the time when we get these problems with b's and k's, they work out the same way as they would have if they're regular numbers, just a little messier, okay? And got to think a little more about some of what you do, but it's still the same situation. Now, yeah, I think it usually will. You'll usually get enough information to know that, yeah. Now, this time, they wanted the x and y coordinates. A lot of times they say, where are the local max and mins? And you just say, well, the local min is at x equals square root of b. Local max is here. But this time they wanted the actual coordinates. So the minimum, or no, they want the maximum. So that would be at negative root b. And then they want the y value. So what do we do there? Put it into the original. Now, this gets kind of messy. Now, here's a problem like this is where, I think I've said this before, where they tell you on the AP test that you don't have to simplify just algebraic expressions. Okay, that's where this might come in handy. So when we do this, it would be okay to just put negative root b cubed minus 3b times negative root b. It would be okay to just leave that as your y coordinate down here and not mess with simplifying. Okay? It would be acceptable. Now, as it turns out, it isn't bad. It's not, I think we should practice it. So if I cube this, I take it times itself 3 times. So this times itself would just be b. No. Square root of b times square root of b would just be b. But, no, times the square root. I'm sorry, I thought you said b squared. So it'd be b, and then times negative root b. So it'd be negative b root b is basically what you get when you cube that. And then this would be positive 3 b root b, right? Now I can add those. Negative 1 b root b plus 3 b root b would be 2 b root b. So that's how it would simplify. Or b to the 3 halves if you want, right? This would be b to the first times b to the half and add the power. So b to the 3 halves if you wanted to do that. That'd be okay. But none of that would be necessary. You could leave it there. Okay, so you do the same thing for the minimum. Now let's talk about d. D says, show that for all positive B values, the max and min points lie on this function. Now, I can't, when you guys graphed this, what did it look like? Did it come up through, somebody got that graph? Somebody got a picture? Okay. So it kind of goes, okay, so it kind of comes up here like this, comes through 0, comes down here like so. That's when B's a 1. The next time it comes up here a little higher, and then it comes down here a little higher, and it does this, and then it goes up here a little higher, and then it comes, whoops, it comes down through 0, and then it comes down here, whatever. Okay, now what we found were these max values and these min values, like so, right? That's what we were just finding. So what they're saying is, they're saying show that these max and min points lie on a function of negative ax cubed. Now, if you look at this, it's kind of easy to see that, yeah, look at these max min points. They do seem to kind of follow if you can do a decent graph. That's what they're saying, is if I graph the whole family of functions here, that these max and min points lie on a cubic function of their own. All right, but all you would do, well, you guys tell me. Anybody got an idea of what we could try here? Well, plug one into these, you mean? But they do say for all values. So you put a 1 in for B, a 2 in for B, and a 3 in for B, found these points and showed that they fit here. But how about just take this, because isn't this all of the max points? How about take this and put it in to there? Into this equation. Okay, so here's my equation for x and y. Because this is the x coordinate of the max and this is the y coordinate of the max. So plug them in for x and y. So let's use black. So I got y equals negative ax cubed. So let's take this and put it in for y. So this is why it would have been nice maybe to go ahead and simplify this a little bit. And then let's take negative root b and put that in for x. Okay? And so I get, and again, this would be 2b to the 3 halves, which would be a nice way to write this. And this would be, now if I cube this, now remember this is b to the 1/2 power here, and I cube that, what do you get? B to the 3 halves, right? Now it's a negative. If you cube a negative, it's still negative. So negative times negative is positive. So this is going to be A, and then what do we say that would be? B to the 3 halves. What do you notice? A would equal 2. Carly, is that what you got? You get A equals 2. But you see how you wouldn't have to put a 1 or a 2 or 3 in for B. You could just put in that point and show that it works. Now you should show the max. That shows that the min values are on there. Then you should take whatever coordinates you get for your max values and plug that into that equation as well. Okay, because what this is the x and the y of the max and mins, and they're saying that that lies in that curve. Well, if it lies in that curve, it's got to be able to be plugged in for the x and the y in that equation. So you plug them in for the x and the y, and you solve for a, and you get a equals 2. Okay? All right. So, that's a good one. You know, a lot going on there, but the heart of the problem was local max min, number line stuff. All right. What else? We got time for a few. If you got some other questions? Yes.
How does finding A show that works?
What that showed when we plugged those coordinates in for the x and the y, since the b canceled out, right? Because what we ended up with was the equation. We ended up 2b to the 3 halves equals a b to the 3 halves. What that shows, since the b's canceled, it shows that no matter what b is, right? No matter what b is, that a always equaled 2. Okay? Because the b's canceled out. So that means, and since we put it into this equation, I guess I don't know what to say other than it showed that the a is always 2, and so it always solved this. And so I guess anytime you're talking about why are these points on an equation, it's because those are the points that make that equation work, right? So like if I graph y equals x plus 2, why is it a line that looks like this? It's because every point on that line, when I plug it in, makes the equation true. And so that's what that's doing. That's what that's doing. Okay? And we know it's every point because it was all b value. We just left b in. All right, what else? Yes?
Do you have to do the number line for different graphs like that? Like in terms of square root of b?
For part D,
Or can you just look at the graph and you really have to do a number line?
no, I'm sorry, are you talking about B and C?
Yeah.
Yes, good question. That was the other thing I wanted to mention on this too, and I did, so I'm glad you said that. Part B said, find the x and y coordinates of the relative max points of F in terms of B. So, I see what you're saying. Since you've already graphed this thing that looks like this, and when you solved your derivative, you got negative root B and root B. You know by your picture that the max is the negative one. And you know from your picture that the min is the positive, and that's what you're saying, right? So did you have to do a number line to show that? That's a great question. I've never seen this, and this is a practice test, and I've never seen this in where they've actually graded it. You know, now I spent a summer grading, or part of a summer grading AP test one year, and so I have a pretty good feel with how they grade. You might be right. You may not have had to do a number line, but I will tell you this: this is a rarity where you have a graph and then you do this. Most of the time, when you find a local max min, it will say, this is what I talked about in the other class, it will say justify, and you will have to do a number line, and what I failed to mention earlier is when you do the number line, that's not enough, right? That's when you also need to say, hey, since f prime is changing from positive to negative at negative root b, then you have a local max. You have to actually say that, and I was lenient on our last quiz with some of your number line. You'd have to say that. So I'll talk a lot more about that before a midterm about making sure you do that when you do a number line. This is a rare one where you've already drawn the graph, so you already have an idea of which one's the max, which one's the min. So you're right, probably would not have to do the number line since you've done the graph. But it was good practice for us because most of the time we don't see this. And I know we're going to run into a lot of problems that have B's and K's and that kind of stuff in them, and I wanted you to see how I did that number line. Okay? So thank you for that. Good question. All right. Any others? Next question. All right. Differential equations. Now, sometimes they will have a free response problem where they tell you to solve the differential equation. And then they want you to use it later on, like in this one. But oftentimes they just have you verify. Here's why. Because they're afraid you're going to screw it up. Now, we don't know how to solve this one yet. This is in the category of ones we don't know how to solve. But later in the year, we will be able to solve this one. Sometimes they'll say just solve this differential equation. But then if you screw it up, then it's hard to use it the rest of the problem. So they'll give you the solution, tell you to verify. Well, that's where we did the T-chart. That's where we did the T-chart. So here's what that would look like. So you would say, okay, I got y prime here, and I got y minus y squared over x here. Okay? So, they're telling me that that's a solution. So what that means is I would have x, so I'm going to substitute now. On this side, I'm going to substitute for y. So I'm going to put x over x plus c minus, and then I'm going to have this squared, y squared. Well, the square of the top would be x squared. Square of the bottom, that would be x plus c quantity squared, right? Everybody see what I'm doing here? So I squared, so I got y, and then I got y squared. And then that's all over x. Now you guys have more room. You can put it down in the one where you've got space if you want to. Okay, over here I need to put y prime. How do I get that? I have to do the derivative of y here. Okay, so let's do that over here. So let's do the derivative of this. Now I need a quotient rule probably. Now I could bring the x plus c up if I want to and do it as a product rule. But I might as well do a quotient rule because look what I got over here. I got a quotient over here too. So I want these to match, so I might as well do the quotient rule. So the quotient rule says derivative of the top, which is 1, times the bottom left alone, which is x plus c, minus the top left alone, which is x, times the derivative of the bottom, which is 1, all over the bottom square. So that's my y prime. Now let me simplify that here a little bit. So this would be x plus c minus x. So that's just c over x plus c quantity squared. Now there's not much more I can do with that. So I'm just going to put that over. C over x plus c squared. All right, now I got a bunch of work to do with the right-hand side. Now, how do I put this together? Well, I need a common denominator. What would be my common denominator? I could bow tie. Now you can't square it because that changes it. Yeah, if you have 2/3 and you square it, now you got 4/9, and 4/9 is not the same as 2/3. What I have to do is take the top bottom times x plus c. Now you can bow tie, but then you'd end up with x plus c. It wouldn't give you a least common denominator, so it'd get a little messier. But here's what I would do. I would take the top times x plus c and the bottom times x plus c. All right? So now what have I got? On my top fraction, I distribute that. So I have x squared plus xc minus x squared. That's what I would have. All over x plus c quantity squared. Now what happens there? Now don't forget, I've still got this all over x down here too. Right? Right? All I was doing was the top part of this. And I've got this x down here on the bottom. This is very similar to when we were doing limits and we were having to do common denominators, right? Yep, you got to do that sometimes. So now the x squareds cancel here, right? So I got xc all over x plus c squared. Now bring this x up. I mean, you could just cancel it, but bring the x up and multiply by the reciprocals, how I like to think about it, right? So I'm going to bring that x up. Dividing by x is the same as timesing by 1 over it. And now that x will cancel that x there. And sure enough, I get c over x plus c squared, and it matches. So that's that's part A. We verified that's a solution. Now, if some of you had some more questions, I'll just talk briefly about some of the other parts. It says write an equation of a particular solution. So that means this is the general solution here. The particular solution is they give you an initial condition. So now you just put a 1 in for x, put a 2 in for y, and find c. Okay? So that's the first part of part B. Then you put that c back in there, and then they said now find the value of y prime at 0, 0. Yes, now, but here's the problem. So they say, find the equation of a particular solution at today's point 1, 2, so we find c, we put c in there. Then it says, find the value of dy dx at 0, 0. Well, here's what's weird about this differential equation. You say, well, dy dx, that's my y prime. Well, I got a y prime right up here, but what happens if you put 0, 0 in there? It's undefined, right? You get 0 divided by 0. You have to put it into this version. Well, we have that version right here. right? Here's y prime right here, right? So you go ahead and you find c. Well, okay, you want to do it? Let's do what the heck? We're this far. Let's do it. So let's put a 1 and a 2 into here, right? So we would get 2 in for y, and we'd have 1 over 1 plus c, right? We're just going to put a 1 in for x and a 2 in for y. So we multiply this over to this side. So we get 2 plus 2c equals 1. 2c equals negative 1. C equals negative 1/2. Is that right? So now my equation is y equals x over x minus a half. That's my particular solution. Right? Remember, the solution to a differential equation is the original equation 1. So there's my original equation. That's my solution for this initial condition. Now, they want to know what y prime would be at 0, 0. Well, I already did y prime over here. All I need is to put in my c. What did we say c was? Negative 1/2. So we got negative 1/2, and then it'd be x minus 1/2 all squared. That would be y prime. So now I can put in 0, 0 into that. Well, all I have to put is 0, because all I have is an x, right? So what do I get? Put a 0 in there, negative 1/2 squared would be 1/4. What's negative half divided by a 4? Flip that up, that'd be negative 2. Okay? So sometimes, because there's a slope field down here, sometimes you get a differential equation that looks like it's undefined, so you think the slope's undefined there. No, it may not be. For certain solutions, it may not be undefined. So you got two different versions of y prime. You got the differential equation version, but you also have the derivative of the solution. Okay, B. Or C, write an equation of the vertical and horizontal asymptotes of the particular solution found in B. Okay, this is it right here. Now it's getting messy here now, but this is my particular solution right here. Well, this is good practice for limits, because that's really what asymptotes are about. Vertical asymptotes are the easy ones, so let's do those first. This yellow equation, this is my solution, this is my y graph. What are the vertical asymptotes? When x equals 1/2, because you get 0 on the bottom. So that's a vertical asymptote. But here's the one we struggle with. Horizontal asymptote, which is going to be a y equals equation. Isn't it when what? Now look at this green equation. Horizontal asymptote. No. What's a horizontal asymptote? As x approaches infinity. Horizontal asymptotes are what's happening way, way out here when x goes to infinity. This is a limit problem. We need to do the limit as x goes to infinity. How do we do that? As x gets very large, what's going on here? It's infinity over infinity. How did we deal with that? One way was L'Hopital's rule, but another way was we didn't need L'Hopital's rule. We could just talk about what? High powers dominate. Does the half matter when x gets huge? So isn't this really just x over x, which is 1? L'Hopital's rule was do the derivative of the top, do the derivative of the bottom. Derivative of x is 1, derivative of the bottom is 1, 1 divided by 1 is 1. Either way, you get 1. So the horizontal asymptote is y equals 1. See, that's one of those questions that we struggle with. It should be easy. It should be an easy one to get, but yet we forget what horizontal asymptote means. It's x goes to infinity, and so it's really kind of a limit, kind of a problem. All right, so those are the horizontal vertical asymptotes. Great question, because tons of stuff to review all in this one question. I'm sure you love it. All right, the slope field for this is given below. Sketch both branches of the particular solution that passes through 1, 2. This is another good example of a problem where each part kind of helps you with the next part and so forth. The horizontal asymptote and vertical asymptote should help us here. Okay, we're supposed to be drawing this equation, but we've got a lot of information that we just found out about. We found out the slope at the origin is -2, right? We found out all that stuff, and I hate to lose all this and move this up. So I'm going to try not to. It said both branches. So we've got a vertical asymptote at 1/2. So that's going to be in here. Okay, we can kind of see how that would be. We got a horizontal asymptote here at y equals 1, which would be in here. And we already said it goes through the point 1, 2, which is up here. Here's our initial condition, right? So there's this branch is going to go up along there and come down along here, right? But we also know we've got to have a branch that goes through 0, 0 because of what we did in part B. In part B, we said for this one, the slope has to be -2 at the origin. So that means down here, notice at the origin how your slopes seem to be xing, right? Which way do we want our graph to go? We want it to be a negative, whoops, so I drew it wrong. That'd be a positive slope. So we want, going through the origin, we want to have a negative slope. So we want our graph doing this. So it's going to come up and go here, and then it's going to go down with that vertical asymptote there. So those are going to be my branches, because I know its initial condition is 1, 2, so it's got to go through the point 1, 2, so that's that branch. And then it's got to have a -2 slope to the origin, so that's that branch. Well, a different initial condition could go through the other way. A different initial condition could possibly lead us to go through there the other way, because it would give us a different C value, and therefore the asymptotes would be somewhere different, right? So if I move the asymptotes over, then it's possible I had a branch that went up this way, right? For example, if this was x plus 1/2, I would have my asymptote over here at -1/2. So I'd have a branch coming up like this. Okay? So the different, there's just a lot of good stuff in that problem. And so, you know, we're getting there. We're getting there. We've got just enough knowledge to be dangerous, right? I mean, that's kind of where we are. So hopefully in a good way, we're getting there in a good way. Now we're putting it together, and a problem like this really does help us put this together. So do I expect that you could be awesome at this problem right now? No, right? That's why the scale on the midterm is a little more generous even than it will be at the end of the year when we do our finals than the AP thing. Because we're not there yet, okay? But we're getting there. We're getting there. All right. Let's move on so I can leave you some work time today. So let's get your notes out. And we're going to talk about a couple of theorems here. And then let you work on some homework based on those. And then if you know you're going to be gone tomorrow, I got to get you the next packet. We're going to hand out tomorrow. But tonight it's just going to be some booked homework problems. Okay? And they're not too terribly long either. I'm going to give you a decent amount of time to work on it. All right, so we have 3 theorems yet to learn. That's what we have left in chapter 4. Okay? And 2 of them we're going to do today. So let's just write down the first one. It's called the extreme value theorem. Your book calls it that. But just copy that down word for word. And the reason I want you to copy down word for word is this, and I don't always do this, but I'm going to tell you on next Wednesday's quiz, I'm going to tell you right now, I'm going to tell you one of the questions is going to be on next Wednesday's quiz. Okay? Guaranteed, for sure. One of the questions on next Wednesday's quiz is going to be state the extreme value theorem. State the extreme value theorem. Now, it'd be best to pretty much do it word for word. Okay? Now, you don't have to have it word for word, but you've got to make sure that whatever you do right has the same meaning. And I mean technically, specifically the same meaning. Okay? Now, I'll talk a lot about these theorems in just kind of common sense, ordinary language, but that's not always specific enough, but it helps us understand the theorem. When you have to state the theorem, Okay. All right. It says let f be continuous on the closed interval AB. Sometimes that part is said if f is continuous on the closed interval AB. Then, some of you are familiar with if-then statements, right? The hypothesis and the conclusion. So the hypothesis here is that f is continuous on a closed interval. The title of this section is Why Continuity Matters. So why is it nice to know you have a continuous function? Here's one reason. Because if you have a continuous function and you're looking at a closed interval, which means you have endpoints, then you know that f has to have, and I said assumes, but you can just say has, you know that f has both a max value and a min value somewhere. Now think about it. If you know you've got endpoints, and the function never has gaps or jumps or breaks, it goes from here to here. It doesn't have to have a highest and a lowest point. Has to, okay? This guarantees you have one. Now, it doesn't tell you how to find it. Now, we know how. We look where the derivative is 0, where the derivative is undefined. We look at the endpoint. So we know where to look for the max and min. But the extreme value theorem just tells us it has to have one. Now, here's the kind of questions you're going to have on your homework. Homework's going to say, I wouldn't write this down, but take the function y equals x squared. It doesn't have a maximum. Does that contradict the extreme value theorem? Because it's not a closed interval. Matter of fact, nothing better contradict the extreme value theorem. I mean, if you can contradict the extreme value theorem, then you would be famous. Because it's a theorem. It's true. It's been proven. Good question. Horizontal line from 7 to 9. So we have endpoints. Is that continuous? Does it have both a max and a min? Let's say you had a horizontal line at y equals 8. What's the max value? What's the min value? They're the same. Vertical line is not a function. Vertical line is not a function. Okay? But now back to what I was saying. Why does this not contradict? And actually, you'd say, why does this not contradict the extreme value theorem? And you would say, because it's not a closed interval. The extreme value theorem only guarantees you to have both a max and a min if the first part is there, the hypothesis. Now, those of you that were in programming, remember our example? Well, those of you that were mentally there all the time. What was our example? If, boy, they were really there. If the car.
What?
If your parents make you this promise. Oh. What was it? Oh, they told it. If
I remember it.
If you get an A in calculus, then I'll buy you a car. This was the example. We were talking about if-then statements. The hypothesis is if you get an A. The conclusion is, then I'll buy you a car. So what happens if you get an A? You get a car. Assuming their promise is true. Now, what we were talking about is when would they be lying to you? Well, if you get an A and they don't buy a car, then they lied to you. Well, we're not lying to you here. This is proven to be true. Right? So we're not lying here, so you're not going to ever find this to be false. You're never going to have a continuous function on a closed interval and not have both a max and min. Can't have it. Okay? But the tricky part of that scenario was, what happens if you don't get an A?
Then you get stuck in the car.
Well, right. So when we talk about in programming classes, like, you know what they meant, though, right? You get an A, I'm going to buy you a car. But if you don't get an A, you're not going to get the car. I mean, that's what they meant. But they didn't say that. If all they said was, if you get an A, then I'll buy you a car. If you don't get an A, it doesn't matter. They might buy a car, they might not. But the promise is, it doesn't matter, right? I mean, the promise doesn't exist for that situation. And the same thing's true here. If you don't have a continuous function, or if you don't have a closed interval, then this doesn't mean anything. Now, you still might be able to find a function where you would have a max and a min. And you might not. You might find some parents who would still buy you the car, and some might not. but it doesn't have anything to do with the original promise. Now, let me show you, and here would be an example of a function. No endpoints. So here's an example of a continuous function, but no closed interval. It still has a max and a min. Here's an example of a continuous function with no endpoints that has a min but doesn't have a max. Neither of these bother this at all, because this doesn't say anything about these situations, right? Now, in your homework, you're going to deal with this picture right here. Here's a couple of functions. Now, what do you notice about these two functions? They're not continuous. So the extreme value theorem does not have to say anything about these, but you're going to get some questions where it's going to say, does the conclusion hold? Well, what's the conclusion of the extreme value theorem? That there's a max and a min. So here, is there a max and a min for this function? What's the minimum? Right here. What's the max? 2. So here you would say, yeah, the conclusion did hold. The theorem didn't hold. The theorem doesn't say anything because it's not a continuous function, but the conclusion of the theorem did hold here. There is a max and a min, but there wouldn't have had to be. It just so happens there was, right? What about G? What's wrong with G? There's no minimum. Now, the other class had a little trouble with this, but there is no minimum. Negative 1.9 is not the minimum because you could go to negative 1.99. No matter where you're at, you could always go a little farther. And you can't do 9 repeating. We talked about that, didn't we? Because that's the same as negative 2. If you did negative 1.9 repeating, that's the same as negative 2, which it can't be. So there is no minimum here, but there is a max. But that doesn't violate the extreme value theorem because there were no promises made when the function is not continuous. Okay, so you're going to be asked some questions like that. And that quiz next Wednesday will have some of these types of questions about this theorem that you have right here. Okay, we have one more theorem to do. That's the extreme value theorem. Okay, here's the second one. This one's a little trickier, the wording of it, but once we talk about it, you'll, I think, see what it means. So go ahead and copy that down. Here's the second question I'm going to tell you on the test next Wednesday, and that is state the intermediate value. So you're going to have to state this theorem. Okay, while you're finishing writing here, I'll just read it here. The intermediate value theorem says, let f be continuous on the closed interval AB, or if f is continuous on a closed interval AB. Now notice, it's the same hypothesis as the other. You have to have a continuous function on a closed interval. Now, when you state this is some of the stuff I sometimes get where I said you don't have to use exactly the same words. They don't mean the same thing. I'll get people who will say, if you have a closed continuous interval. Well, that's not right. It's not the interval that's continuous. The function's continuous on a closed interval. I mean, things like that. So that's what I mean by if you reword it, it could be okay, but it might change what it means, and then that would be bad. All right. So if f is continuous on the closed interval AB, and let k be any number between f of a and f of b. Now, it's important to understand that f of a and f of b are y values. Those are outputs. And they're at the endpoints. That's another key part of this. The outputs at the endpoints. K is any number in between them. Then there exists some c between a and b such that f of c equals that value k. Oh, man, what a bunch of gobbledygook. All right. So let's make sense of this. Here's what it's saying, and we actually talked about this the other day. We were doing Newton's method. Remember when we were doing Newton's method, we're looking for a root? We want to know where the function is 0, and we said, let's just plug some numbers in and see if we get lucky. So we plug in a -1 and we get out a 5. And we plug in a 3 and we get out a -2. What do we know?
Every point between those two
But yes, but referencing what I was talking about with Newton's method, we're hoping to find one where we get a zero.
So it's somewhere between F.
Somewhere between here and here, this has to hit zero. And Kelsey, it's because of what you said. If a function is continuous, it has to hit, on its way down to here, it has to hit every y value between them. The only way it wouldn't is if it jumped. But then it's not continuous. It has to, now, does it have to only hit the ones in between there? No, it could go up here, and then come down here, and then come down here, right? If I'm going between here and Gibbon on Highway 30, I have to hit all the points in between unless I beam myself, like from there to there, but then that's not continuous. But I wouldn't have to go just from here to Gibbon. I could go to Shelton, come back, then go to Elm Creek, and go whatever. But if I started in Kearney and ended in Gibbon, I had to hit all the points in between here and Gibbon. All right? Same thing is true here, but it's the end points, and that's the key thing. So, if you want to write this down in kind of layman's terms, then you'd say something like, intermediate value theorem says if it's a continuous function at closed interval, the function has to hit all the y values in between the endpoints. That's basically what it says. Now, on the test, and I say state the intermediate value theorem, you can't just write that. Okay? You better memorize this, or come close to this. I think that's the best way. Don't just say it hits, because hits, what's happening? Okay, you could say the function takes on all the y values between f of a and f of b. If you said something like that, that'd probably be pretty good. Okay? But we know what we mean by hits, but don't write that if you're actually stating a theorem. All right, now let's go back to that picture we had a minute ago. Now, obviously, the intermediate value theorem does not have to be true for these because they're not continuous. But does the conclusion hold? Does it hit all the y values on this first one? Yes or no? You got a gap right in here. Carly, you said yes. Didn't you? Don't let us talk you out of it.
You know, I know it is this though, because it has to be between -2 and -4.
Oh, okay. So when I the endpoints. Okay, now I forgot what my question was. So I'm trying to think if the yeses are right or the nos are right. My question was, yeah. Let me repeat the question. Does the conclusion of the intermediate value theorem hold for f? Yes. The closed interval is -4 to 4, right? That's the A and the B. And it has to hit all the y values between the endpoints. That is f of -4 and f of 4. What's f of -4? What's f of 4? Does it hit all of the y values between these 2 points? Oop, there's a hole there, but it hits it there. Hits it, hits it. Does it hit the y value at 1? Yes. This gap doesn't matter. If you were thinking about this gap, you were thinking about max and min. You were thinking it has to hit all the y values between the max and min. That's not what it says. It says it has to hit all the y values between f of a and f of b. So f of a would be here, and f of b would be here. Starting and ending. Has to hit the y values in between. This one does. What about this one? They have to hit all the y values between here and here. And I think it does. Right? Yeah, the fact that that's open down there doesn't matter. It's not about max and mins. It's about f of a and f of b. Okay? So that is kind of what's going on with this intermediate value theorem thing, and it's a big deal in Newton's method. All right, so your homework is the problems. Actually, we haven't done this for a while, but on the actual Chapter 4 assignment sheet, it's 4.8. 4.8. So you got the rest of the time to work on those. A lot of them just have to do with those 2 theorems. That's all they have to do with, really, are those 2 theorems. Answering some questions, explaining, that kind of thing. These are the types of questions that Wednesday's quiz will be about. Okay? Newton's method, we said, a little bit of that. Monday we'll talk about one more theorem, so it'll be a little bit of that. Tomorrow I'll give you another packet. Okay, go ahead and go to work. Tomorrow will be quite a bit of work time, quite honestly. some of the packet, and then maybe some work time on the take home too.